welcome everyone. We just heard an excellent ITC colloquium by Freeke van der Voort. And she will tell us some more about some elements in simulations of galaxy formation that are made by rapid neutron capture, our process. And then after that, we'll hear from Valentin, who is a student at the Max-Planck-Institute for Extraterrestrial Physics. He's sitting over there. He's a student of Andy Berker that visited us a few weeks ago. And he will tell us about primordial black holes in the solar system. After that, we'll hear from Akash Gupta from Princeton. Where is Akash? Oh, over there. Who will tell us about from the galactic to atomic scale, understanding planet formation and evolution. And finally, we'll hear from Yufeng from the University of Wyoming, who will tell us about the self-supervised learning method for the identification of bad exposures in large imaging surveys. Freeke, you can start.
Thank you very much. So yes, rapid neutron capture elements are half of the elements that are more massive than those in the iron peak are made through the rapid neutron capture, and the other half through slow neutron capture. And we are still not entirely sure what the cosmic sources are that make these types of elements. So people take a variety of approaches into trying to learn more about what can make rapid neutron capture elements. So I cannot actually, I cannot resolve any of these sources. I work with cosmological simulations. Our resolution is usually like 1,000 solar masses or something. But what I can do is study galaxy structure, galaxy dynamics, mergers, the full 13 billion years of star formation and interactions, etc. So, and see if we come up with a good distribution, or a realistic distribution of what these sources might be, what then comes out later on when we look at the stars that these simulations produce, and what how much they are enriched in our process compared to other metals. So these are observations that I got from the Saga database, and you can see this is in metallicity abundance ratio units. So these are bracket notations, and it means that they are normalized to solar as well as logarithmic, even though the logarithm isn't specifically specified. But that's what that means. So you can see it with the red arrow I've drawn. You can see that the scatter at low metallicity, these are extremely metal poor stars, is huge, many orders of magnitude. And this has been used to argue quite successfully that europium, which is a very pure R-process element, and then by sort of extension, all rapid neutron capture elements are produced by a very rare source. And the problem is, does it actually work? So what we do is we put a very simple initially, this will get more complicated soon. We put a very simple delay time distribution based on what we think as a reasonable approximation for what neutron mergers do in the real universe. So after a stellar population forms, for the first tens of millions of years, there won't be any neutron star mergers because you have to wait for 2 supernovae to go off and then for the neutron stars to spiral in by losing energy through gravitational waves. And then this falls off at something like 1/time, but it could be a slightly different time dependence as well. And then this results in about 10 to the minus 4 neutron star mergers per year in a Milky Way mass galaxy at redshift 0. Which is highly uncertain, of course, compared to our Milky Way, but there are some estimates based on binary pulsars that are sort of in the same ballpark. But it could also still be an order of magnitude lower or higher. Neutron star mergers are likely, so the binary likely gets a kick from the first supernova that goes off, because supernova explosions are never perfectly symmetric, which means that if the binary is not unbound, the binary will travel at potentially hundreds of kilometers per second until the merger eventually happens, and this can then happen well outside of the galaxy. So if we assume a kick velocity of 200 kilometers per second, which is on the high side but not unrealistic, then after a minimum delay time of 30 million years, it will already have traveled 6 kiloparsec. After 100 million years, it will have traveled 20 kiloparsec. A galaxy like the Milky Way is tens of kiloparsecs large, but of course there's no reason for this kick to happen in the disk direction. It's most likely to happen away from the disk. So now these neutron star mergers are not exploding in the galaxy itself, but they're exploding around the galaxy, and then through gas inflow, these elements have to make their way back into the ISM in order to become part of future generations of stars. And stars are the only sources that where we have information about our process elements. I don't think we've detected it in gas. So here are, again, all of the observational data points I could find at that time compared to what this simulation then looks like. So I would, the caveat is that this is a collection of different surveys. It's not a perfectly unbiased sample. It's just everything that's in the literature. Maybe some non-detections weren't published, etc. But if we take them at face value, the black line shows you the median values in our simulations, and then the blue points are all the detections and observations. And I think you would agree that it doesn't seem to match that well. So this is just for our first guess attempt at doing a delay time distribution in any stellar population in our simulations, and then following the full 13 billion years of evolution. If we, however, tweak this delay time distribution that I told you about before, then, so I just say, okay, they happen slightly earlier, and it doesn't depend as 1 over time, but actually as 1 over time to the 1.5. So now it's a steeper distribution. That means that more neutron star mergers will go off fairly soon after a star particle has formed, therefore will be more closely connected to the ISM and have a less long delay from coming back from the halo gas into the galaxy. So this matches relatively well. However, if we now switch off these 200 kilometer per second kicks, if you compare these two simulations, the dark band is the 1 sigma scatter compared to the cyan dashed lines is the observational scatter. You can say that the scatter is now not set by how rare these objects are. It's now set by this additional kick that they get when the first supernova explosion goes off. We've now made this more complicated by, instead of using a simple delay time distribution, like I said before, we use the neutron star merger rates from binary population synthesis calculations, which of course are also uncertain by themselves, but we just wanted to see what happens if we do something that's potentially more realistic than our just random simple guess. And then this is the result. So at high metallicity, it seems to work relatively well, but at low metallicity, we don't get enough enrichment to get enough stars to sort of solar abundance ratio levels for extremely low metallicities that form all at redshift 4 or higher. However, if we look at only the solar metallicity stars, so these are ones that are within 0.1 dex of what the sun has, then we can see that the relation between age and our process abundance ratio is fairly well matched by this particular model. So there's a slight negative trend towards old ages. If I now go back to that model that seemed to work fairly well with a very steep delay time distribution, so on the right is that basically reproduced, and then on the left you can see what the age relation looks like for solar metallicity stars, and now we actually have the opposite trend compared to the observed solar twins. So that's approximately all I have time for. I just wanted to say that we are trying to use neutron star mergers in order to explain the observed stellar abundance ratios of our process elements, and we're not having a very easy time with it. It's definitely not something that comes out very naturally. So if the delay time distribution is fairly steep, then the kicks can help increase the scatter. We can match the Milky Way distribution, where we're having some trouble for solar twins if we use a delay time distribution with a time dependence of -1. Then we don't match the low metallicity stars, but we can match the solar twins. So maybe we need multiple sources, maybe we just need a different source altogether, not neutron star mergers, or maybe there is some aspect of the rate in which neutron star mergers happen that is like a metallicity dependence, for example, which binarity could easily depend on, that could help us explain the distribution of our process elements in the universe. Thanks.
You were assuming that the mass function of stars is not evolving, but in reality we expect many more massive stars at low metallicities, and that could obviously help you. The other question, I mean, we do see metallicity-age relation in galaxies, or radius metallicity relations. You could use that in addition as another observable that you could learn.
Yeah, you're right. There is some metallicity dependence for our binary population synthesis models. So here is the very low metallicity and solar metallicity compared, but it's not a huge difference. And yeah, no, I haven't used the radial relation. I don't know how much we know about our process elements in that space.
Thank you. Comments? Go ahead, Tony.
So if I remember correctly, isn't the escape velocity from the Milky Way something like 550 kilometers per second?
I don't know that either.
Oh, well, so, I mean, that
yes,
would...
someone says yes.
It is 500. Near the sun, it is 500.
Yeah, so anything going off at 200 kilometers per second never gets out, right? It's got to come back eventually.
Yeah. Yes, which is fine. But we needed to come back. So so all these extremely low metallicity stars, they form redshift 4 and higher. So this is when the universe is like 1 billion years old. So we needed to come back efficiently, like within a short enough amount of time, in order to enrich enough of the extremely metal poor gas with our process elements. So in a way, having the enrichment with, for example, iron decoupled from the enrichment with our process is good, because now you can have an iron-rich pocket and an R process-rich pocket, so you can still make some of these stars. But if it takes too long before they come back, then we're only forming stars with a metallicity above -2, and that's fine for reproducing those stars, but doesn't help us with reproducing the observed ones with very low metallicities.
Any other questions, comments? If not, thank you so much,
Yeah, thank you for giving me the opportunity to speak here at the ITC Lunch. And I'm Valentin. I'm a PhD student in Munich in the group of Andy Burkett, and today I want to talk about I think very fun little project that I did together with my supervisor, focusing on primordial black holes. And today I'll talk about and argue why if these objects make up the entire dark matter. Oh, what's happening? Oh. Then maybe they'll have the event rate to occasionally fly through the solar system, and we can maybe detect their gravitational perturbations. So primordial black holes have been first discussed in the 1960s and then later 70s by Seldovich, Novikov, and later Stephen Hawking. And at that time it was also realized that those objects could serve as an alternative dark matter candidate in comparison to the usual scenarios where you have WIMPs or any kinds of particles. And especially lately, after the first gravitational waves have been successfully detected with LIGO, there was an enormous increase in attention to that field, because now it was becoming possible to have a new pathway to also measure dark matter if they are in the form of these objects. So just as a very brief summary, primordial black holes are coming from the idea that we have some probes of the primordial power spectrum on very large scales, but we do not know for most of the part what is happening on much smaller scales. And if there are any density fluctuations introduced during the period of inflation, they inevitably collapse into black holes if they reach a certain threshold that is essentially that blue line. And in that case, they can produce the entire dark matter. Now, phenomenologically, you can put constraints on the fraction of dark matter in these primordial black holes, here as the parameter f. And that has been done for a long time, and there's various ways to probe these. So here are, for example, constraints from gravitational lensing, cosmological and dynamical constraints, gravitational wave constraints, constraints based on Hawking evaporation. Now, so far, the region with the least constraints that seems the most promising is this window around here, which is sometimes referred to as the asteroid mass window. The mass range is something like 10 to the 17 to 10 to the 23 grams, so it's actually fairly heavy compared to most asteroids, so it's on the heavy end if you compare it to actual asteroids. And those objects, black holes in that mass range, have Schwarzschild radius which are below 10 to the 7 meters, which is the reason why we don't have, for example, the lensing constraints there anymore, because they are simply shorter than the wavelength of visible light. You can also look on the other end. Hawking radiations is also difficult to probe at those masses, simply because they lose a very small fraction only of their mass over cosmological timescales. However, it gets interesting if you look at actually what is the number density or dark matter objects at those mass scales. So for 10 to the 20 gram, right in the center of this mass window, you have about 1 within, let's say, the planetary region of the solar system. So in the past, there have been some ideas how to constrain that asteroid mass window, like collisions with white dwarfs, captures by main sequence stars. But based on that number density, and also inspired by a research note that Avilib published in the fall of last year about the influence of primordial black holes in the solar system, we were interested to actually study if those objects, if they are apparently present at those mass scales in the solar system as a dark matter candidate, what consequences would follow from this. So essentially, the idea is you have your solar system depicted here, and then with a certain event rate, depending on the mass, these objects will fly through the solar system and perturb the orbits of planets just by a tiny little bit, which is exaggerated here, of course, for this illustration. And so what we did for this study is essentially we studied simulations, simple n-body simulations of the solar system with the sun, the planets, Earth's moon, and embedded it into such a dark halo with a local dark matter density. Then the dark matter has a velocity distribution, a random component, and then you also get that dark matter wind because the sun moves on its circular trajectory around the galactic center. You get a root mean square velocity that is on the order of 60 AU per year. So these objects do cross the solar system with within a fairly short time. For our simulations, to keep things simple, they actually also move on straight trajectories and have periodic boundary conditions, which is fairly okay because they have these very high velocities and are thus not really impacted at all by the potential of the solar system. And then you run essentially with random initial conditions for positions and velocities, this very often. So essentially that you fill your phase space of essentially how the perturbations can look like. And then the relevant quantity that you look at is essentially the vector between Earth and the solar system object and how that changes if you introduce PBHs. So essentially, how the PBHs affect orbital distances between solar system objects. And the reason why this is the interesting quantity and why this might be worth studying at all is that we do have very precise data on a few solar system objects in terms of their distance, simply because we have orbiters going around those planets. For Mercury, Moon, Mars, and Saturn are the objects where we can achieve up to 10 to the minus 12 to 10 to the minus 13 in terms of the observational accuracy. So that's fairly good. It's maybe not as accurate as, for example, LIGO can measure relative distances, but so indeed it's a very good precision. Now, because Mercury has out of those the strongest relativistic effects, and for the Moon you have the finite size effects with the Earth, for our simple simulation it's best to look at Mars because it will be best described simply by our approximation of having just the Newtonian gravity and point masses. So it will be our most ideal candidate to study. And anyway, so the residual is very similar for the other objects, as you can see. So first, over a time span of 1 year, you can look at essentially how those perturbations behave for different PBH masses, making up the entire dark matter. So this is here the relative perturbation of the vector between Earth and Mars here. As it grows over time, as more and more flybys happen, and you also get occasionally a more close flyby. You see the blue lines are the simulations. They, of course, have a spread because, of course, your impact parameters have a distribution. But what you see is if you compare the values between the different PBH masses, that within this asteroid mass window, it's not super sensitive on the PBH mass, simply because if they are 10 times as heavy, then the gravitational acceleration is 10 times more, but also the event rate is 10 times slower because the number density goes down by a factor of 10. So then focusing on a 10 to the 20 gram PBH scenario, we ran a few thousand simulations over a time span of 20 years. That's roughly the time for which we have precise data for Earth-Mars distances because we had the orbiters for that time. And the result is you get a displacement, a median displacement on the order of a couple of centimeters, which is just about an order of magnitude shy of about the observational accuracy that we have. So first of all, that means that you cannot directly rule out 100% dark matter in the form of PBHs based on this effect. But being just one order of magnitude shy, it's conceivable to think that this could serve as a probe, essentially, a gravitational probe of the existence of dark objects in the solar system. To summarize this, so the perturbations themselves are too small to directly rule them out as 100% of the dark matter with the current data. But since we are about one order of magnitude away from the current observational precision, it's conceivable to think that actually the solar system could serve as a gravitational probe for this kind of scenario in the future. But there are a few things that need to be addressed in order to do this, and that's also something we are still working on. For example, you then need to have much more high accuracy models that actually are able to really take into account all of these effects that are used for these predictions of solar system ephemeridess that I mentioned briefly, relativistic effects, finite size effects, and so on. And then you need to show that the effect that that the PBHs produce is not strongly degenerate by other things. So for example, the total mass in the asteroid belts or the mass of the planets, their initial position and velocities are all free parameters that are fitted when these models of solar system are created. So we need to make sure, need to study whether this effect still pops out, can still be detected, or essentially disappears in the solar system fits. And then the final question is, if you actually observe such a thing, then of course you need to look for it because it could also be another, it could be a non-PBH asteroid flying by, which you then need to distinguish optically. Yeah, so I'm at the end of my talk now about this topic, and if you're interested, you can scan this for the paper, and otherwise I want to thank you for your attention.
Valentin, would you like to say a few words about gravitational wave detectors like LISA within the coming decade? I mean, how well will they do? That will be a different sensitivity curve than you were alluding.
Yes, so there is a bit of work that has been done on LISA to essentially be used for the same purpose. LISA has a smaller arm distance between the objects than Earth and Mars, and that corresponds then probing ideally a smaller PBH mass, and that is also related to how long essentially the gravitational wave detector can stay coherent. So you want to essentially have the flyby happen on a time scale and a frequency that the gravitational wave detector can measure. And I believe it's on the order of 10 to the 15 grams where LISA is able to probe these PBHs. So it's essentially complementary to this. So Earth Mars has the best sensitivity somewhere around 10 to the 19, 20 grams, what I've just shown you. But yeah, the gravitational wave experiments are in a sense complementary to that.
I was wondering at what point the internal structure of the planet becomes important in sense of this accuracy.
At what point? Sorry?
The internal structure of the planet becomes important. We can get
the finite size of the planet, he's asking.
So I mean, the flyby parameters that you have at that mass window over conceivable time scans or event rates that you can observe, they never cross the planet, if that's the question.
No. I mean, I would assume that because of the planet has a finite size and homogeneitis, right? So you can have finite accuracy of the center because of this, right? The gravitational center.
The impact parameter is much larger usually than
yes.
the
size.
So it doesn't matter.
Yeah, no, I understand your question. No, in principle, this needs to be accounted for. I mean, when we measure the distance to the orbiter that goes around Mars, we effectively measure the barycenter of Mars because that's what the orbiter is flying around. But indeed, yeah, if you want to essentially compare, the data that we have to a scenario with PBHs, you need to take into account all these effects, which is done essentially already in solar system models. So. There's a model by JPL, NASA, there's a one by Paris Observatory. They do include like all those relativistic corrections, they include finite size effects for all the planets, and yeah.
But the shift in position is much smaller than the size of the planet. We're talking about a meter versus. So I guess, how do you know exactly the centroid location of the planet? I guess you measure the light emitted by the planet to some precision. But, so when you measure the effect, I guess that was the question, right?
No, I thought you said that it's from satellites, right? All those satellites are orbiting the Earth.
I think those are two different questions, but yeah.
I think we're asking the same thing. So you're saying that the position is accurate to 1 meter from Mars, like the barycenter. Yeah. So the question is by how much this 1 meter will be affected by inhomogeneitis of the planet itself.
So okay, yeah. No, for Mars the finite size okay, get it. So for Mars the effect of the finite size is lower than the 1 meter. So for Mars there's two things. There's observational accuracy and there's just how well the models can even predict those orbits into the future. And for Mars the main uncertainty is mass in the asteroid belt to Earth distance, not the finite size effect.
Okay, last question. Go ahead.
Yeah. To detect this kind of primordial black holes, Is it possible just if you look at the diagram to see, you can see some occasionally flare of the photometry of the stars and to see some brightness effect into detect? Is it possible?
I couldn't understand it all. I need to look at
Microlensing.
microlensing.
Yeah. Is it
Okay.
possible?
So these objects
the
are.
problem is the Schwarzschild radius
Yeah.
here is less than the size of an atom. So then when you calculate the Einstein radius, it's the geometric mean of the Schwarzschild radius and the distance. And that is smaller than the wavelength, I guess, or not even smaller than, well, it's a very small
Yeah.
scale, the Einstein radius, so the cross-section is negligible.
So with visible light, it's not possible to do lensing beyond the point that is shown here, right? You see those purple constraints? They end at around here, which is exactly where the wavelength becomes comparable to.
I think it's finite source effect, the fact that the star, the angular size of the source is actually bigger than the Einstein radius. It's not so much the wavelength, it's the angular size of the source being, so then the Einstein radius is lensing just a small fraction of the star, which makes the effect not detectable. It's not the wavelength. Anyway, thank you so much, Valentin.
Hi everyone, I'm Akash Gupta. I'm a 51 Pegasi fellow at Princeton University. Oops. Sorry about that. Is this better now? So yeah, today I would like to share with you how we can understand the planet formation and evolution process from the galactic to the atomic scale. And what exactly I might add, let us see. And now, before I move on, of course, this is just not my work, but it's thanks to all these my number of advisors and collaborators who have contributed to it. Now, the typical Earth to Neptune-sized planet accretes a primordial hydrogen-dominated atmosphere. How do we know this? A number of ways. First of all, exoplanets. Today we know, I'm sure a lot of you have seen this figure already, that by the way, y-axis is number of planets, x-axis is the size of the planet relative to Earth. So the highlighted region is what we today refer to as the super-Earths, the rocky planets in our galactic neighborhood, whereas these are referred to as the sub-Neptunes, the gas-rich planets apparently. And what we have come to realize is that atmospheric loss processes can explain these observations. Idea being that your typical planet starts with a hydrogen-dominated atmosphere. Some of them lose that atmosphere over time, becomes rocky planets. Others keep it. And in this way, these atmosphere loss processes can actually very well explain the observations. So on the y-axis, we have planet size, x-axis, stellar mass. And on the left hand, you have the model based on particular atmosphere loss process. On the right-hand side, California Kepler survey observations. Similarly, we can also make predictions about how things would be around if you were looking at FGK stars and M dwarfs. And not just this, we also have, of course, evidence from our own solar system, of course. And we also have protoplanetary disk observations showing us the same thing. So in a nutshell, planet formation process entails this interaction of the hydrogen with the interior of the planet from millions to billions of years, but still your typical model ignores any interaction between these, these constituents. So we should ask, are these interactions even important for us to care about? Should we just ignore? Is that fine? And studies are already showing not quite. What you expect in the atmospheres that you might see with JWST, for instance, very much gets dictated by what's happening inside these planets. It can even have impact at the demographic level, And in general, like at a more fundamental level, how these planets thermally evolve and their internal structures. And these questions are more important today because of, thanks to JWST, because now we do have observations that are helping us put much better constraints on these planet atmospheres. And here's one example of JWST observation of TOI 270d. And the main thing I want to just focus on here is that the inferred mean molecular mass of the atmosphere is like 5.5, which is definitely not a hydrogen atmosphere, right? Similarly, we have evidence for this. Studies have suggested that Earth might have had a primordial atmosphere perhaps, and Juno measurements have shown the same thing for Jupiter, that such interactions could be happening deep down in this planet. So again, whatever your favorite planet might be, these interactions are important to understand to really contextualize observations from JWST or the future habitable worlds or Uranian orbiter. But when you're working with these kind of models, you very quickly realize that we actually have a very poor understanding of how these interactions actually happen. And if you think about it, our fundamental understanding of how these planets work, our models can only be as good as our fundamental understanding of how these planet building materials actually interact. Issue is that laboratory experiments are pretty tricky, but quantum mechanical methods can help on this front. Specifically, I've been employing the method of ab initio molecular dynamics, something that is used across the fields of engineering, science, medicine. And here we are trying to understand, for instance, something I will be focusing on today is the hydrogen-water system. Why? Because not only can this give us insight into planets in our own solar system, but also help us figure out in our search for water-rich exoplanets or that could harbor liquid water oceans. Because frankly, we do not know how these if you can have a liquid water ocean or not on many of these planets, because we do not have understanding of the relevant processes. There are other efforts also that are going on, like Austin Go, an undergrad working with me, has been looking into the hydrogen ammonia system. We're looking into how things might be on rocky planets and how the interaction deep down in the planet could also be impacting some of these observables in the atmosphere. But again, coming back to this, typically the way we think about these Neptune-like planets is that water-rich planets is that, there might be a hydrogen-rich layer sitting on top of water, or that there might be some composition gradient. But again, we do not really know what the reality is. Something that could help us get around this is to figure out something called critical curve of these mixtures. The idea behind which is something like this. Y-axis is temperature, x-axis is pressure. Critical curve basically divides this parameter space into regions where hydrogen and water will be completely mixed, like the hotter side, and the cooler side where they will be not completely mixed. So let us have a look at the data. Again, temperature y-axis, pressure x-axis, log scale both. And this is how the experimental data looks like. And this blue region is where we expect the atmosphere to water boundary to be in the Uranus-Neptune case, for instance. And experiments are only exploring 3% of this space. And so we went ahead and figured out how these these interactions are like at these data points. And what we find is that the critical curve looks something like this black dash curve. First of all, we can see good agreement with the data. So at this point, let us try to figure out some planetary scale implications. So let us just clear out the plot. There were too many things before. So again, y-axis temperature, x-axis pressure. The black dash line is all that we need to think about, which is the critical curve, dividing the regions into the gray area where hydrogen and water mix, regardless of what proportion you put them in the blue area, they sort of partially mix. For context, here are the Neptune Uranus temperature pressure profiles from Nettleman et al. 2013. And something interesting is that they're strikingly close to each other. And that tells you that mixing of hydrogen and water are likely very important in Uranus and Neptune today. I'm not going to go into more details about this, but this has some very intriguing implications for their evolution and what could be happening on these planets today. So now think about this orange, reddish adiabat of a young Neptune or hot sub-Neptune, a young Uranus or hot sub-Neptune. It completely lies in the region where you expect hydrogen and water to be completely mixed. So if you're looking at a hot enough exoplanet, and if it is water-rich, you actually expect its entire atmosphere to be completely like a mixture of hydrogen and water. And this gives clues, like physically motivated clues to understanding some of these recent observations we are getting of high mean molecular weight atmospheres. Now, as this planet cools, it will eventually intersect this critical curve, and that is when, first of all, in the very outer regions, you will have clouds will start to form. Eventually, it will intersect deeper down, and that is when you will start to get this rainfall deep down in the planet, something that could be happening in Uranus and Neptune today. And that also tells you that you have to be beneath this curve or intersecting with it for there to be a water world, for there to be an ocean underneath some hydrogen atmosphere or Hycean world or something like that. And so it really helps us narrow down where the future surveys could be looking at for these water-rich planets. Beyond this, there are also some fundamental properties that we get insights into, like molecular to atomic transitions that could be happening in these planets deeper down, which could give us some insight, which could be consequential for the envelope or interior opacities, the electrical conductivity or the magnetic field generation of in Uranus and Neptune. But at the end of the day, these are new fascinating insights, but we need to put them together and try to understand how do planets actually evolve given all these new insights. And Roberto Tejada has been leading the effort in this direction by leveraging an in-house planet evolution code called Apple and trying to understand what would happen if we do include all these new physical and chemical insights on what happens in these planets. So just focusing on this particular plot, y-axis temperature, x-axis pressure, what he's finding is like something interesting that when you do take into account these things self-consistently, there are some issues with reproducing the current observations of Uranus and Neptune. What that tells you is that maybe it is important for Uranus and Neptune to have some primordial gradients itself, like compositional gradients itself. But further on, there are other issues also with these kind of studies, which is that each of these dots that you're seeing here is something like 10 years of CPU time, like a single CPU time, but still. And so we have been working on making this process much more simpler and much faster by working on this, to automate this entire process of figuring out atmospheric interactions via machine learning driven quantum mechanical simulations. But of course, I'm almost basically out of time, so this is something for the next time. I hope I meet you. But to summarize, interaction of planet rebuilding materials are consequential to what happens in these planets and are important for understanding the observations from JWST, the habitable worlds, or the Uranian orbiter, and their planning. Experiments are hard, but quantum simulations can help us. And through these computational experiments that I just shared with you about hydrogen water, we're finding some really cool insights into Uranus, Neptune, existence or constraints on the existence of exoplanets with water or not, and also some new insights into the fundamental properties of how materials actually work at these extreme conditions. And that is it from me. I'd be happy to answer any questions. Thank you so much.
So, Akash, first, quantum computers might be very helpful for you in the future. You could probably do much better. But my question is more about, as you lower the temperature, eventually you get to a situation where water becomes ice, right? So then you will separate them, right? And then wouldn't you lose the hydrogen at that point? Or?
Yes, absolutely. So if we just go back a little, oops. So if we just stay on this plot. So here I did not try to focus today on this, but here I've drawn in blue the water, the phase diagram for pure water. So on the left hand side you have supercritical water. On the right hand side you have crystalline ice in different phases. So this phase basically lies underneath the critical curve for hydrogen and water mixtures. So at first there will be this separation. The composition of the outer atmosphere might change because of how hydrogen and water demix even before water crystallizes. So that will actually precede, but eventually you are right. Eventually you will end up having crystallization, and you might have ice crystals falling down. Or actually, what is more relevant for something like Uranus and Neptune is that its core might start to grow, and that might have implications for the different modes that you're finding in the Uranian satellite systems and those kind of things.
So when you say ice crystals, here in Boston we call them snow. Anyway, yeah, please.
This is very interesting. I was wondering whether you can say a bit more on the actual quantum chemical calculations. and whether you can apply this methodology to H2 formation on dust grains, and in particular the detachment of the formed H2, because that is a critical question for H2 formation in the interstellar medium, and the rates that we are using are 60 years old. And if there is an update, that would be greatly appreciated.
So here I'm basically doing molecular dynamic simulations. So I'm not using, I'm not doing some, so yeah, so that is what I'm doing here. So I'm not actually using some previous.
And stuff like that.
Sorry?
It's not quantum mechanical Hartree Fock on the quantum level.
It is, but I'm using the density functional theory in this case. And one thing is definitely true, that while this is much more sophisticated than people extrapolating to orders of magnitude, which often happens to understand what is happening with these planet building materials, there are like approximations that you have to consider when you're using density function theory, for instance in terms of exchange correlation functions and so on. And that is something definitely we are all like always wary of. And on that front, we do need more experiments on this front. And there are folks working like at the Laser Energetics Lab or the Lawrence Livermore Lab working on this in this direction. Regarding the dust, I know that there's some people who have started working on this front, but at the DFT level even, it's just too expensive because the dust grain is usually much bigger. I know that there have been some efforts from the Roberto Carr's group in Princeton, in the chemistry department, the physics chemistry department. They have tried to understand nucleation in Earth's atmospheres. But again, those calculations are like extremely, perhaps, unless I'm like misunderstanding what you were exactly saying.
No,
but
I don't want to take too much time, but for my question, you don't need to model the entire dust grain, but just the site where the H2 molecule has formed and sits and detaches.
Okay.
It would be much more linear calculation.
Okay. Yeah, it would be interesting to. I recently looked up, saw a paper that came out on like Nature Communications in this regard actually. So it would be interesting to see what methodologies they have employed. I have not played around in that direction, but yeah, it would be interesting to chat more on that front.
We need to move on, so let's thank Akash again.
Okay, thank you for holding on to the last talk. Hello, everyone. Thank you for having me. My name is Yufeng, and I'm a fourth-year PhD student at the University of Wyoming. And today I'm going to talk about the semi-supervised learning method for identification of bad exposure in large image survey. Okay, when we always talk about many of the large surveys, especially for large imaging surveys, we probably want to talk some examples. Some of them we know is PenSTARRS and DES. And we know the LS is coming online. It can actually survey the whole sky in 3 consecutive nights. Then we have lots of data, especially lots of exposures. It's very critical for us to really identify some of them, what are good, what are bad. In the past, we could probably do it by visual inspections, and that can be very time-consuming if we have large number of bad exposures. So I want to first talk about what are some maybe examples of bad exposure and some kind of, for example, we could have bad exposures caused by instrument issues or weather or pupil ghost or satellite. So all the exposures I'm showing here are from the deckhand. And the first one is more like a transparency issue. And sometimes we have the ghost pupils where you can see that's where I have the internal reflection of the white stars here. And also we could also have satellites and hopefully not UFOs and leaving the strikes. So many cases are like that could be solved, could be addressed by existing pipelines. So how to really identify them? The traditional method, we could have observer's log. Of course, if you observe, you could log what is really the weather condition, what are some really bad reasons why it's bad. Or after a data reduction, you could also have visual inspection campaign, which can be time consuming, but you can really have the ground truth answer to it. Or you could have photometric measurements. For example, we could have a 0-point measurement to see whether the point is really bad, or we have a PSF problems. And more advanced ones, for example, have ray tracing algorithm developed by for DES to really find some of the scatter light. And of course, beyond traditional method, we also have machine learning-based answer. So some of them, I would say the first one is a mass region-based convolutional neural networks. It's actually for low surface brightness galaxies. They developed that pipeline. And there's another one that developed specifically for the DES that's actually on the ghost and scatter light issue. But for our pipeline, we are more interested in using less human intervention. Then we have to imply some method called self-supervised learning. So what is self-supervised learning? First of all, it's no human real label required. It's actually generates self-supervised learning signal by itself. And one of the pipeline we use is called Dino, which even have no labels in its name. It's called self-distillation with no labels. And it's pre-trained using 142 million images in ImageNet. So ImageNet, as some of you know, is actually it's not only include, it's very diverse. It includes many kind of examples. Oh, some of them get cut off. It's basically, for example, the first one is supposed to be a bald eagle, and can be dog, cats, or even boots. But we actually do some transfer learning from ImageNet to DCOS using some transformation of our data. I also want to talk a little bit more about what actually Dino can do. For example, it has two branches. The X here is basically an image, and X1 and X2 are the two views of the image. Usually X2 is a global view. For example, if we have a cat, then probably we would feed X2 as a whole cat, and X1 will be maybe a cat's eye. So that's the image information from different level can be passed along. Okay, our pipeline is basically self-supervised training VAT plus supervised learning k-nearest neighbor. That's why it's a semi-supervised learning, because first part is self-supervised and second part is a supervised one. For our data, we have DKLS, DR9 and DR10. They are CP processed, because usually for DACAM, it can be either processed by a community pipeline, which CP stands for, or it's using DES's own pipeline. And for k-nearest neighbor labels, we have three sources. One of them is the bad exposure list. That's actually mostly from the observer's log, which the actual log, what are some information when they observe, what kind of conditions they have. And also we have DES delve list. Those are actually two visual inspections experts label. And I will talk about two analyses. The first one will be on using the clustering analysis to really see, without any label, self-supervised way, what can be learned from the information. And then the second one, of course, is basically the classification results. So for the clustering analysis, what we do is using a PCA analysis, which is to reduce the dimensionality from the original 384 to 15, and then we use t-SNE to further reduce to 2 dimension. And the axis itself doesn't really represent anything. It's just used for visualization. Specifically, there's two things we want to get from the plot. First of all, there are some clear clustering that we can see. For example, we know the cluster transparency, they actually reside some part near here in the bottom part, and some of them, for example, the baticity usually occupies the top right part. But some of the cases, for example, the ghost scatter, which are very complex, they actually overlap quite a lot with the good cases, which we don't really want that case. So then we actually do a further analysis to see what actually each cluster, if we do a self-clustering, what can we find? And also I have this 3D interaction plot. If you're interested, you can scan it. It's actually inspired by Professor Alyssa Goodman's work on this one. So yeah, please go ahead. For the clustering analysis, what we do is using HDB scan, which stands for the hierarchical density-based spatial clustering and application with noise. So we do find actual 70 clusters for the whole image data set, and here I only show 25 of them for those two cases. Specifically, we can see some of the clusters are actually very apart, separate apart from the main clusters. So we pick actually 3 clusters from here and 3 clusters from here to really understand what their difference are, why some of them are actually very separated, why some of them are not. Then if we look at them, we pick some examples from the clusters on the top and on the bottoms. So most of them, they all have a ghost scattering. That's usually the people ghost here we show. But the one problem is that for the bottom one, we just really overlap with the main cases, with the good cases, is that this one is not supposedly to be a ghost cluster case because it really doesn't have the ghost signal. It's only have a little bit maybe a satellite trails over here. and that's a case. So that actually means we can find bad exposures and using this method, and with probably very high accuracy. That's what we expected to see. And for the classification result, that's what we eventually get down to using the labels. We have 12 categories. 11 of them are bad. One of them are good. One of them is good. And most of the clusters or categories are self-explaining. Only the N objects and wonky. The N objects are actually from the DES processing pipeline. It basically means some of them have many ghost sources, could relate to noise or scat estimation issue. Or wonky is basically the other case, which there's something definitely wrong with exposure. We just don't know why. So we want to really figure out. So wonky is more like cases that observers don't really understand why, and we try to figure out. And most of the cases, we have very high accuracy, and except for the good and ghost cluster, which is because, as you see, they actually overlap from clustering plot, and also they are very complex. On the other hand, if you're interested, you could also ask me later why the wonky is 1. It's supposed to not be 1 because this cluster is very inclusive. It's including all the cases. And in conclusion, we developed a semi-supervised learning framework using VAT and k-nearest neighbor, and we also did some analysis on the clustering and the classification. Performance looks quite promising for us. So we have about 100,000 new exposure from DECAM for our campaign for DR11, and we identified 1,700 bad exposures candidates, and then we confirmed eventually 700 of them are bad. So the manuscript on this work is soon to be submitted. I also want to talk about really, I'm thankful for my advisor, Professor Adam Myers, as a board, and also for Professor Alex Rilico-Wigner sharing the DS and DELP labels. And I really want to also thank my collaborators and the imaging, legacy imaging team. And thank you so much for listening. I will take any questions.
Thank you, Yufeng. Any comments, questions? Please.
You show that you can actually isolate exposures affected by clouds.
Yes.
But there is this thing that sometimes looks similar to clouds, but in fact it doesn't. It's the air glow, which sometimes can be at a scale of 1 degree or less. And like Archimedes, sometimes you see stripes moving at relatively high speed through the sky. And the difference with the clouds will be that it wouldn't affect transparency. It will just raise the background. Will we be able to distinguish between the two?
Well, yeah, that's a good question. It depends on whether CP can actually, the community pipeline can remove cases like that. There's 2 ways I can answer it. The first one is from more the survey design point. For example, for us, we actually only look at very deep part, we care about depth. So some of the exposures in that case might already be excluded from even our exposure. So that's the first part. And the second thing is about using CP. Because our exposures, we actually do the training and navigation after the community pipeline. So if community pipeline actually correct for things like that, we don't really even have a chance to look into it.
Of course, for the Rubin Observatory, it would be good to know the coordinates of all the communication satellites,
Yeah.
Starlink and so forth.
Yes.
Because then you can take those streaks out of the data set immediately.
That's definitely one of the cases, and I think the similar cases for Pan-STAR where they actually have to know sometimes where the satellite could be and to really avoid it. And I believe they may already develop a pipeline to actually patch part of the satellite out.
Well, in fact, the U.S. Space Command told the Rubin Observatory people that they have a small computer program that they need to apply to the data before anyone looked at it, just because there are classified satellites out there. So some of them will be taken out by the government.
Right. Yeah.
Anyway, let's thank Yufeng again.